last time. Let me know if you have any questions as I go. But this is sort of the level of math we're going to have in this class isn't going to get really any higher than this stuff. If this stuff makes okay sense, you're great. But you know, again, this is just sort of a reminder. If this stuff looked really foreign to you, we should just talk about whether this class is the right class right now. Okay, so the first one was to plot the function y equals x squared. This is actually a function that's going to be pretty important in this class, quadratic function. You can do this by remembering the shape, or if you don't remember the shape, you can choose a bunch of x values and then plot xy coordinates. But it's a parabola opening up like this. The second one was to calculate the slope of the line that went through the points 1, 2, and 4, 3. So I'm going to draw those points out. 1, 2, you go 1 over in the x direction and then 2 up in the y direction. So there's 1, 2. And then 4, 3, you go 4 over in the x direction and then 3 up in the y direction. So something like that. And we're looking for the slope of the line that connects those two. So what's the slope of that line? Well, the way to do that is that the slope is equal to the rise over the run. So the rise is the change in height as you go from one of those points to the other one. So how much higher are you at point 4, 3 than at the point 1, 2? You're 1. You know, you can think of that as 3 minus 2. And then the run is how far you've gone horizontally from the one on the left to the one on the right. It doesn't actually matter which one you call your starting point and which is your ending point. It just matters that you're consistent. You call the same one the starting point for the rise and the run. So your destination horizontally is 4. Your starting point is 1. And so you get 1/3. And so if you have a line with a positive slope, that always means that it's tipped up from horizontal. Okay. If you have a line with a negative slope like this, if this came out negative, it would mean that line was rotated down from horizontal, or I guess clockwise from horizontal. Then question 3, simplify the expression a times b squared times c squared all over b to the 4th times a times the square root of c. I'm going to rewrite this as a times b, because b squared is just b, times c, and then on the bottom, that's b, and then a, and then I'm going to rewrite this c as, this square root of c as c to the 1/2 power. Okay, so now we can cancel a bunch of stuff. This a cancels this a. 2 of the b's in the numerator cancel 2 of the b's in the denominator. And now, there's a couple of ways to think about canceling the c's. I guess you can use an exponent rule. That's one way to do it. If you have, so the exponent rule for division says if you have something to the m power over the same thing to the n power, that's equal to x to the power of m minus n. And so using that, I'll write this as, so all that stuff on the top canceled except those c's. And on top, I'm going to use the exponent rule. Since I already wrote it out as c times c, I'll call this, this c here, that's c to the first power. This is c to the first power. And then c to the first power divided by c to the 1/2 power is c to the power of 1 minus 1/2. So you're left with 1/2. So we get c to the first power times c to the 1/2 power over, we still have b times b. Now I'll bring this down here. The exponent rule for multiplication says if you have the same thing, well, let me write it. So, exponent rule for multiplication, says if you have x to the m power times x to the n power, that's equal to x to the power of m plus n. And so I can rewrite this as 1 plus 1/2. I can, that's c to the power of 1.5, or I'll write it as 3/2. And then b times b, what's left in the denominator is just b squared. So that's about as simple as you can make it. Any questions about that one? I guess any of them so far? Okay. And then number 4, we want to solve this expression for a. We have this this equation that says a squared times b times c is equal to 4c plus b squared times c squared. We want to get a by itself on one side of the equation. So first I'm going to divide everything by b times c. So we get a squared is equal to Everything on the right side needs to be divided by b times c, so I'll write that as 4c plus b squared times c squared, all divided by bc. I guess I'll cancel this b with oh no, can't cancel the b's, we can cancel the c's. So I'll cancel this c with this c and one of those. And then I'll take the square root of both sides. You get a is equal to 4 plus b squared times c all over b square root. And that's almost the complete answer. There's one thing I'm missing. That one thing that's kind of interesting, kind of cool when you see this stuff, the stuff that you've done in math classes come up in physics, is at least I remember when I was taking algebra and whatever, where we did this kind of stuff, some of the rules seemed a little abstract to me. We're going to actually see, everything that has a mathematical answer in physics, there's sort of like a physical interpretation that corresponds to it. And so the one thing I'm missing here so far, always at first felt just sort of like an abstract thing, like but with physics, we'll see that it sort of corresponds to actual physical things. Okay, what is it I'm missing? When you take the square root, so when you take the square root of both sides, if this, okay, so what happens if a was -3? You'd square it and you get 9, and that would say that this is equal to 9, right? What if a is equal to +3? You square it, you get 9. So you lose some identity when both sides are squared like that, because whether it's a positive number or the corresponding negative number, you get the same thing when you square it. And so the answer needs to be, so a has to be equal to plus or minus that square root. Either one of those solves that equation. And when we start talking about projectile motion, we'll see that when we have problems where you have to do a square root like this to get the answer, the plus solution and the minus solution each have physical interpretations that are totally different from each other. Okay. And then the last one is solving a system of equations. We have these two equations. The first one was x1 plus x2 is equal to 50. And the second one was 2x1 minus 3x2 is equal to -10. And there are various sort of clever ways to solve these, but just substitution always works. So might as well just always do that. You'll always have plenty of time in this class. So what substitution means is we're going to use one of these equations to, so for example, I'll use equation 1 to represent the variable x1 in terms of the variable x2. So subtract x2 from both sides, and you get that x1 is equal to -x2 plus 50. And then I'm going to plug that in to the second equation. So in the second equation where we have the x1, I'm going to replace that with -x2 plus 50. So what I'm doing here is substitution. So we have 2 times the quantity negative x2 plus 50 minus 3x2 is equal to negative 10. And now I'm going to multiply everything in the parentheses by 2. So we have negative 2x2 plus 100 minus 3x2 is equal to negative 10. I'm going to subtract 100 from both sides. So we have negative 2x2 minus 3x2 is equal to negative 110. Negative 2x2 and negative 3x2, we can add those two coefficients together, and we just get that negative 5x2 is equal to negative 110. And then divide both sides by negative 5, and you get 22. X2 is equal to 22. Okay, are we done? Almost. We did the hard part, but now we just have to figure out what x1 is, knowing what x2 is. Which one of these equations can we use to do that? Since, we started with these 2 things, and we knew those were true, as long as we didn't make any mistakes, everything else is also true. So we can just go to whatever equation makes it easiest to find x1. I'll use this one right here. So x1 is equal to negative 22 plus 50. I'll use this one. X1 is equal to negative 22 plus 50. So that's equal to 28. Any questions about that one? Okay. So now we're done with the intro. Now we can start with the first part of this class, which is unit conversion. And every quantity that we measure in physics has some kind of units associated with it, and the meaning changes completely if you change the units. So physics measurements need units. So, for example, if someone asks you how far is it to the store, and you say 6, that doesn't do any good, 6 could mean a lot of things. You have to associate that with meters. You'd be really close to the store. They should probably see it if they're 6 meters away, or it could be 6 miles, So, for example, 12 feet is a measurement of distance. And all of the measurements that we're going to use in this class are going to be made up of 3 fundamental types of measurement. So all our units will be made up of 3 fundamental unit types. And those are distance or length, time, bless you, length, time, and mass. And pretty often we're going to, at least at the beginning, we're going to be given measurements in one unit, and we'll want to convert it to a different unit representing the same fundamental type. So you're pretty used to doing this in everyday life, you know, like how many inches are there in 3.5 feet, you know. But we're going to have to do it with more complicated combinations of units, meters per second, kilogram meters per second squared. And so we're just going to come up with a sort of a careful mathematical way to do this. And I think probably you've done, most of the people who take this class have taken chemistry before. You don't have to have, but so most of you have done this in chemistry before. But we'll often want to convert a measurement using 1 unit to a measurement in another unit of the same type. So for example, how many inches are there in 3.5 feet? Inches and feet are both measures of length. So, you know, it wouldn't make any sense to say how many seconds are there in 3.5 feet, but these are the same type, so that makes sense. And the way we're going to approach this mathematically is we're going to say 12 inches is equal to 1 foot. Okay. And one way to think about that is if you divide something by itself, you always get 1 back. So let's think of 12 inches divided by 1 foot as being equal to 1. And that's also equal to, you know, you can switch which one's on top and which one's on the bottom. And either way, that's equal to 1. And the thing about 1 is you can multiply anything by 1 without changing what you started with. Okay, so if we're trying to, we don't want to change the actual length that we're representing. You know, we want to represent 3.5 feet no matter what. Okay, we just want to use a different unit to represent it. So we're going to multiply 3.5 feet times one of these two ratios. Since they're both equal to 1, it won't change anything. Okay. So we have 3.5 feet. And I'm going to multiply it by 12 inches divided by 1 foot. You know, multiplying 1 doesn't change the quantity. And then we're going to think of the units themselves as being algebraic variables. And since we have feet in the numerator here and feet in the denominator here, we're going to cancel those out. And now we have a number 3.5 times a number 12 times a unit inches. The numbers, when you multiply them together, you get 42, and so the answer is 42 inches. Okay, but what if instead of multiplying by 12 inches over 1 foot, I'd switched the order and multiplied our starting value by 1 foot over 12 inches? So what if we multiplied that starting value by 1 foot divided by 12 inches? Okay, so let's do that. So we start with 3.5 feet. And then we multiply that by 1 foot over 12 inches. Now nothing cancels. You have 3.5 times 1 divided by 12, and the units are feet squared over inches. That comes out to be 0.2916 repeating. Feet times feet, or feet squared, inches. It's not wrong, except that we weren't asked for that unit. I mean, that's a usable unit of length. It just isn't the one we wanted. Feet squared over inches. So how do we make sure that we always multiply by the ratio that we want? This is not the units that we wanted. So what you want to do is always multiply by the ratio that cancels out the unwanted units. Okay, so let's look at the one that worked the way we wanted it to. So we started with 3.5 feet, and then we multiplied by the ratio, and we're always going to be multiplying by these ratios that are equal to 1, a ratio of two things that are equivalent. We multiplied by the 1. This started with feet in the numerator. We multiplied by the ratio that had feet in the denominator. So the feet here and the feet here canceled. And we were left with the unit that we wanted. Okay. The second one went wrong because we started with feet. We multiplied by a ratio that didn't cancel feet. And now we have this crazy combination. Okay. So what you're going to want to do is just always choose the ratio that cancels the thing you're trying to get rid of. And by the way, I'm going to just always use this shorthand. This shorthand notation. So what I did before was 3.5 feet in parentheses times this fraction, 12 inches divided by 1 foot. instead of writing out all those parentheses, I'm going to just write it as 3.5 feet with fraction bar, and where the parentheses come in, I'm just going to write that. I'm just going to write those as a vertical line. Just saves pen strokes. A few of these will, be pretty long because you'll be canceling out a lot of different units in these combinations. And so up here we have 12 inches. Here we have 1 foot. So this means the same as that without quite as much writing. Saves a little time. Any questions about that? Okay, so let's do one now that a new example. And this time, let's say that we want to convert, we want to express 61 miles per hour in meters per second. Okay, so the starting value is, 61 miles per hour is really 61 miles divided by hours. That's what miles per hour means. And we're going to use two facts. We need a relationship between miles and meters, and 1 mile is equal to 1,609.344 meters. So if you ran the mile in high school, you really were 9.344 meters short, by the way. I always want to see people at high school track meets, like, they run the 1600, not the mile, but I always think it'd be cool if somebody just like ran 9 more meters. Like, I'm not a quitter. I came to run the mile and I'm going to do it. Anywho. And then we also need a relationship between hours and seconds. So 1 hour is equal to 3,600 seconds. Okay, so our starting value is 61 miles divided by hours. So 61 miles divided by hours. And it's going to be the same process as it was before, except we're just going to have to do it in 2 steps. So we're going to have to multiply by one ratio that converts miles to meters, and then multiply that by another ratio that converts hours to seconds. Let's do miles to meters first. We're going to use the ratio either 1 mile over 1609 meters or 1609 meters over 1 mile. Which one do we want? So miles are in the numerator here. We're trying to get rid of miles. We're trying to go to length units of meters. So we want the miles in our ratio to be in the denominator, so it cancels. Get rid of the unwanted units. So we're going to put 1609.344 meters in the numerator and 1 mile in the denominator. And you can see that those cancel the way we want them to. And so if we multiplied this out now, the number we would get would have units of meters per hour. But we want meters per second, so now we have to cancel out that hours. We're going to use either 1 hour over 3,600 seconds or 3,600 seconds over 1 hour. Which one do we want in this case? We want the hour on top to cancel the starting hour in the denominator. So 1 hour on top and 3,600 seconds in the denominator. So that hour cancels that one. And now, if you look at what units are left, you have meters in the numerator like we want, seconds in the denominator like we want, so that's perfect. Now all we have to do is multiply out the numbers. So 61 times 1609 divided by 3,600 is 27.26 meters per second. You can also do these conversions sort of in a step-by-step process. So like, for example, let's say you didn't know there were 3,600 seconds in an hour. You knew there were 60 seconds in a minute and 60 minutes in an hour. So if you didn't know 1 hour is 3,600 seconds, but you knew that 1 minute is 60 seconds, and 1 hour is 6 minutes. You'd start the same way, 61 miles per hour. And you'd first convert miles to meters just like you did before. So 1609.344 meters over 1 mile. But now you don't have a way to convert directly from hours to seconds. So what we do is first convert hours to minutes and then convert minutes to seconds. And you can do it all in this same equation. It's not an equation, but the same fraction. So to cancel this hour, we have 1 hour up here, and we know that's equal to 60 minutes. And then we want to cancel the minutes, and we know that 1 minute is equal to 60 seconds. So this should be miles. So these cancel. The hours cancel. Minutes cancel. And if you look at what units are left, you have meters in the numerator, seconds in the denominator, so that's what we want. And now you just multiply all those numbers out and you get the same thing. Any questions about that? Yeah.
Like doing decimals, how many numbers should we go up after this?
Decimals? Yeah. I don't care about significant figures. I don't know. So just keep a few decimal places. I don't know. I think I usually keep 2 decimal places on things unless it's a really long number and I get bored of writing, or if it's smaller than 1 and then I keep 3 decimal places. But I don't care what you do. Just, you know, I would care about that if chemistry teachers didn't care so much about it. But I know like your chemistry teachers are going to make you learn that stuff, so here you don't have to worry about it. Yeah, I don't know, just round them however you see fit, basically. Yeah, I don't care. Because I'm sure your chemistry teachers made you, like, if you really thought about it, you could do it, so we won't worry about it. Okay. So let's do one more example. So let's start with express 38,640 yards per minute squared. We're going to do it into two different units of the same type. This type of unit is a length divided by a time squared. We'll do it for feet per second squared, and we'll do it for meters per second squared. Okay, so we're starting out with 38,640. Oh, and let me give the conversions that we're going to use too. So we know that 1 yard is 3 feet. And this one you might not know off the top of your head, but 1 meter is equal to 3.281 feet. And then we'll use the fact that 1 minute is 60 seconds. Okay, so for part A, we're starting out with 38,640 yards divided by minutes squared. I'm going to write that as minutes times minutes. And the approach I'm going to take is I'm going to convert the yards to feet, because first we're trying to do this as feet per second squared, and then I'm going to convert minutes to seconds. Okay, so to convert yards to feet, do we want 1 yard over 3 feet or 3 feet over 1 yard? Yeah, we want 3 feet over 1 yard because we want to cancel yards. That's what we're trying to get rid of. So the 1 yard goes down there. The 3 feet go up here. And once we multiply that out, we'll be in length units of feet. And now we want to do the minutes. Do we multiply by 1 minute over 60 seconds or 60 seconds over 1 minute? 1 minute over 60 seconds. Okay, so now I cancel. This minute cancels. It doesn't cancel both of those. You can pick one or the other, but so what that means is we're not done yet. Even though we've done a conversion from yards to feet, and we've done a conversion from minutes to seconds, if we multiply these numbers out now, we have units of feet per minutes times seconds. Okay? So we're going to have to use this conversion one more time to cancel out the second minutes. So 1 minute over 60 seconds, that cancels the other one. And so now you can go through, pick out the units that are left. We have feet over seconds times seconds. So now we finally have the units that we want. Multiply this all out, and someone multiply that out. I don't have that in good detail. 32.2 or so, right? 32 point. Can you give me a couple of decimals? Oh, okay. 32.2 feet per second squared. Yeah, if you have a way that you're comfortable thinking of it, keep doing that. You don't have to follow my way, but this is a way that makes sense to me. And if you haven't settled on something yet, here's one that works. But yeah, I don't care how you do this. If you know how to do it, keep doing what you're doing. Okay, so part B. Now we want to convert to meters per second squared. We could use either of these two as a starting point. Might as well use the 32.2 feet per second squared. So we have 32.2 feet, and I just always, we're not going to convert seconds, but I'm just going to write it as seconds times seconds anyways. So to cancel the feet, do we want to multiply by 3.281 feet over 1 meter, or 1 meter over 3.281 feet? Yeah, we want the feet in the denominator, so it cancels this. And then 1 meter up here. And so now we're in units of meters over seconds squared, and that comes out to 9.81 meters per second squared. This one, not so much, because we're not going to use units of feet very often, but this one is something that we're going to see all the time. Anybody happen to know what that number and that unit stand for? Yeah, that's the acceleration that gravity causes. That's the acceleration of gravity for an object in free fall. So if you're in a vacuum, or if you have an object that isn't affected very much by air resistance, and you drop it, that's what its acceleration is. You know, I'll talk about what acceleration means and stuff like that. But this is going to be a really important number in this class. And we're going to call this the little g. So here's something that might not immediately occur to you as a conversion problem. You can think of it as a conversion problem. And I want you to see if you can think through this. You can talk to each other about it or whatever. You're not going to turn this in, but just sort of try to practice this stuff. So let's say that you started with, so you have this box. It's a cube, and all of the lengths are 1 meter. How many centimeter cube boxes could fit inside? Okay, so we're talking about like there's one, there's one, there's one. Okay. So you take these little boxes that have side lengths 1 centimeter, and you could fill this box with those. How many of those would fit inside? So yeah, take a minute, see if you can make any sense out of that, and then I'll talk about it. But yeah, talk to each other. Talk about to each other about how much you hate doing stuff like this. So you can think of it as a conversion from 1 cubic meter to cubic centimeters. So your starting quantity is going to be 1 meter cubed, and you're going to want to convert that to cubic centimeters. Okay, using the fact that, so you want to convert to centimeters cubed using the fact that 1 meter is 100 centimeters. Okay, so we're going to start with 1 cubic meter. That's 1 meter times meter times meter. And we're going to multiply that by the ratio, either the ratio 1 meter over 100 centimeters or 100 centimeters over 1 meter. We want the meter in the denominator to cancel these. So we'll go 100 centimeter over 1 meter. That cancels one of these. So you can see we'll have to do that 2 more times. 100 centimeters over 1 meter. Cancels another one. And then one more time, 100 centimeters over 1 meter. Cancels the last one. And so now the units that are left are centimeters times centimeters times centimeters. So multiply out the numbers and you get 1 million centimeters cubed. So to fill a box where, you know, a square cubic box where all the sides are 1 meter long, you'd have to put 1 million of these little 1 centimeter cubes inside. Any questions about that? Yes. I will always give you, I'll always give you the conversions I want you to use. You know, they won't always be like the most direct way, but there'll always be enough to do it, I might make you do it in multiple steps, you know what I mean? Okay, in this class, we'll mainly use SI units. And the SI units, the unit of length is meters. And we'll represent that with a lowercase m. The unit of time is seconds. That's lowercase s. And the units of mass are kilograms. And that's lowercase kg. But the fact that we're going to do almost every problem in this class in combinations of these three units brings up the need for the next thing we're going to talk about, scientific notation. Because we're going to do physics problems sometimes where we're dealing with tiny, tiny amounts of like things that are such a tiny fraction of a meter that if you wrote it out in standard notation, you'd have 13 zeros before the first number. And that's a pain. And even worse than being a pain is that it would be easy to get off one and you're counting, and maybe that doesn't seem like such a big deal, but that means you're multiplying your answer by 10, And if your answer is off by a multiple of 10, your answer is way, way off, So we're going to often want to use scientific notation. And the idea of scientific notation is that any number can be expressed as one non-zero digit and then a decimal point, and then a decimal, and then times 10 to the power of some integer. If you're talking about numbers that are way smaller than one, like the one that I just said, where you have 13 zeros, a decimal point, then 13 zeros, and then the number, this integer is going to be negative. And if you have things that are way bigger than one, well, maybe that are any bigger than one, then that's going to be a positive integer. Okay, so for example, 3,481 in scientific notation is 3.481 times 10 to the third. Ten to the third power is 1,000, so it's 1,000 times 3.481. Or negative 0.0036 is equal to negative 3.6 times 10 to the 1 to minus third. So you can write any number that way. One thing that's useful about scientific notation is, there's a little bit of ambiguity. Well, there are rules for how many significant figures a number has. And like I said, I'm not going to talk much about significant figures. But the rules can be a little cumbersome to remember. Like, does a 0 count as a significant figure? Well, if you remember, it doesn't count as a significant figure if it's before the decimal point and there aren't any other non-zero numbers after it. Okay, so that's a little complicated. And it always counts as a significant figure if it's after the decimal point. But rather than having to remember these sort of tricky-ish rules, if a number is expressed in scientific notation, every digit before the times 10 to the whatever is significant. That's how many significant figures you have. So like, this one, how many significant figures do you have? 1, 2, 3, 4. This one, how many significant figures do you have? This one would probably, until you get really used to it, would take a little more thinking. You'd have to like, what do you do with those zeros? But once you write it like this, it's just 2 significant figures. So we're going to need to be able to do 2 things. We're going to need to be able to take a number in standard notation and write it in scientific. And we're going to have to be able to go the other way, start with a number in scientific and put it in standard notation. So that means there's 2 methods that we need for going between standard notation and scientific notation. Okay, so for the first one, let's say we want to we write this as we want to go from standard to scientific. And the example I'm going to use here is negative 541.6. So the first step, count the number of places and I'm going to call that number of places n, that you need to move the decimal place left or right so that from that starting number, you have 1 non-zero leading digit. Okay, so in the case of this example, our one non-zero leading digit is going to be that 5. So how many places do we have to move the decimal from where it is to just having the 5 before the decimal place? 2. And do we have to move to the left or the right? Left, yep. So in this case, n is equal to 2 and move to the left. And then the second step, the last step, is if we moved left, then we have times 10 to the positive n. If we moved right, we have times 10 to the negative n. So in this example, we have negative 5.416 times 10, and since we moved to the left, it's positive 2. Any questions about that? And then the other thing that we'll have to be able to do, is go from scientific notation to standard. And the example I'm going to use here is 6.52 times 10 to the negative 4. We want to express that as in standard notation. And so the first step is take the absolute value of the exponent, that's what we're going to call n, and the sign of the exponent. So in this example, n is equal to 4, and the sign is negative. And then the last step is, if the sign is positive, move the decimal point n steps to the right. If the sign is negative, move the decimal point n steps to the left. Okay, so in this example, we're going to move it 4 steps. Since the exponent was negative, we're going to move it 4 steps to the left. So we have 6.52 I'll write it like this. And we started with it here. We're going to move 1, 2, 3, 4. So there's the new location of the decimal point. All these get zeros. And so that's the number in standard notation. Any questions about that? Okay. One more thing I want to mention. That's prefixes for units. For example, what I'm talking about is like kilometers. A kilometer is the prefix kilo attached to the unit meters. What are some other ones? Microns, that looks like micrometers. Think of it as micrometers, but people say microns. Centimeters, that kind of thing. All these things are prefixes that have a meaning when you associate them with units. So these are the ones that we're going to use a lot. Micro, and when people write it in an abbreviated form like that, they use the Greek letter mu. It's sort of like Greek letter mu is spelled mu, and it looks like it's in between an M and a U. That's how you can remember it. And the meaning, whenever you see this, you can just replace that mu symbol with times 10 to the 6th. No, times 10 to the negative 6, sorry. So that's the meaning of it. And so if you see 50 microns or 50 micrometers, you can think of that as 50 times 10 to the minus 6 meters. Okay. Then milli is represented with a lowercase m. That can be a little confusing because we're not talking about meters and it has the same abbreviation, but that's times 10 to the minus 3rd. Centi, that's a lowercase c. That's times 10 to the minus 2. And then kilo, that's a lowercase k. That means times 10 to the positive 3rd. And there are a few I'm skipping, but these are the ones that are going to be important in this class. And mega, that's a capital M, and that means times 10 to the 6th. Okay, so for example, how many meters are there in 17.5 kilometers? Well, the K in kilometer, or the K representing kilometers, means times 10 to the 3rd. That was one of the things I said up here. So if you start with 17.5 kilometers, you can just replace that k with times 10 to the third. And then that's equal to 17,500 meters. Or how many millimeters no, let's go the other way. How many meters are there in 50 millimeters? Okay, well, we're starting with 50 millimeters. The milli means times 10 to the minus third, so that's 50 times 10 to the minus third meters. And so that's equal to 0.05 meters. Okay, so both of these examples that I did there, I was going from something with a prefix to something without. If you're starting with something with a prefix, going to something without, it's easy, you just replace it. If you're going the other way, you're going from something with no prefix to something with one, then you have to think of it as like a unit conversion. So, like, for example, how many microns are there in 0.20 meters? Okay, so now we're starting with something with no prefix. So what we have to do is think of it as like a unit conversion. So one micron is equal to 1 times 10 to the minus 6 meters, based on the meaning of that micro prefix. And so now we're going to do the unit conversion, 0.20 meters. We're going to multiply it by either 1 micron over 1 times 10 to the minus 6 meters, or the reciprocal of that. We want the meters to be on the bottom to cancel the meters here. So we have 1 times 10 to the minus 6 meters is equal to 1 micron. The meters cancel, and you get 1, 2. So that's going to be 2,200, I think, microns. Yeah. So in 0.2 meters, there's 200,000 microns. Any questions about that right now? Yeah, that's right. So that's the same thing as multiplying by 10 to the 6. That's it. We've gotten through enough stuff now to do a few problems. So look on D2L tomorrow, and there'll be some problems assigned.